કેમ છો બધા? So next chapter is rotational motion. So here I have clubbed three chapters. First one is center of mass, second circular motion, and third, so that is rotational motion, which includes moment of inertia. So from JEE or NEET point of view, this chapter is very important. Normally, you will find three questions in the NEET exam and two questions in the JEE exam. Okay, so now and the somewhat difficult chapter of the mechanics, so that is rotational motion. But if you will do the practice simultaneously, then you will not find any problem. In this chapter, focus on the concept. Okay, so I will give more stress on the concept. If concepts are clear, then you can solve example very easily and develop your visualization pathway. Okay, so now you can see here, identify the rotational motion. Okay, so now if we consider this mass, then motion of this mass is, so that is linear motion. Okay, so motion of the mass is linear motion, but motion of this wheel, so that is about this axis, so that is rotational motion. You can see motion of this object, that is also rotational motion. Okay, but now this object has two simultaneous motion. Okay, so if we consider the center, if we consider the center of the object, okay, if we consider the center part, then center move along the straight line while this object, okay, revolves about the axis. Okay, so this motion is called a special type of rotational motion, that is rolling motion. Okay, and here you can see the most of this, okay, motion of this device, that is called rack and pinion. So rack, so motion of the rack, that is linear motion, but motion of the pinion, so that is rotational motion. Okay, so now you can imagine the rotational motion. So before we discuss the rotational motion, so first we will discuss the concept of center of mass. Okay, so first we will discuss the concept of center of mass. So center and mass. Okay, so it means whole mass is concentrated at a single point. So that point is called center of mass. If I want to apply a Newton's law of motion to our body, can I apply? So where I have to apply it? So that is a question. Okay, because mass out of the body means there are so many parts and motion of independent particle is different. Suppose you are riding on the Activa. Okay, so now if I want to study the motion of the Activa, then motion of the wheel is different, motion of the front and back wheel is different, motion of the body is different, motion of the person is different. So now where I have to focus? Okay, so to understand this body, okay, so first, or to understand or to analyze the various forces or various terminology or various physical quantity, okay, so we will first identify the center of mass. Okay, so first let us discuss center of mass. So before we discuss the center of mass, first we will discuss rigid body and flexible body. So now first one is rigid body. So you can consider this body. This body is rigid body. In which case, so if we consider number of particles, okay, if we consider number of particle, okay, if distance between the two particles or separation between the two particles remains constant irrespective of the forces which are applied on the object, then it is called rigid body. So body is said to be rigid if separation between any two adjacent particle does not change on application of external force. So when we apply the external force, so distance between two particles if remains same, then this object is called rigid object. Okay, so most of the time most of the objects are rigid object up to some extent. if we consider the rubber or eraser, so when you press it, so its shape remains same? No, there is a change in shape as well as size of the object on because of application of force. Then rubber or eraser, we cannot say it's a rigid body. Okay, so for rigid body, size and shape does not change. Yeah. So rigid body, a body which does not change its shape and size after application of force. So that is called rigid body. So in rotational motion, we are assuming the object is rigid. Okay, but there is no perfect rigid body in this world. Okay, so up to some extent, we can consider this body is rigid body. So same thing we will discuss in elasticity. Okay, so now example, you can see this fan. Okay, so you can consider this fan as a rigid body. You can consider this potter. Okay, so this wheel you can consider as rigid body because there is no change in here. So here we are changing the shape. Okay, here there is no change in shape on application of, but here shape continuously changes. So this is not rigid body. Okay, here we are changing the shape. Okay, so now you can consider this fan is rigid body, while this, if you consider this wheel, so that is rigid, but this pot, so pot is not rigid body. Okay, so now consider this wedge shape and consider a block. Okay, so block slides from top to down. Okay, so now consider there are two forces. So now observe this motion. So this motion is which type of motion and which physical quantity is constant. Okay, if you consider the motion of independent particle or motion of all the particles, so now you can see motion is translational motion. Motion is translational motion because motion of all the particle is same. Velocity of all the particle is same. Okay, so let's block sliding down the inclined plane. So you can consider, so inside the particle, all the pump are moving together. It means they have same velocity at any instant of time. Okay, so if I want to study the motion of this body, so motion of all the particle is same. So instead of all the particles, I can study the motion of any one particle, and this particle represents the motion of whole body. So that is also possible. Okay, so but here the all particles move together at constant velocity because this body is rigid body and motion is translational motion. So this is pure translational motion and all the particles moves at constant speed. So now consider sphere. So sphere is a rigid body. Yes, sphere is rigid body. Now observe the motion. So now in this motion, so this motion is translational motion. Yes, object moves from top to bottom. So motion is translational motion. But additional to it, okay, now all the parts are also moving around one center point, okay, about the axis of the object. Okay, so this motion includes not only translational motion, it also includes something else. Okay, so but all the particles are not moving with same velocity at instant of time. So all particles are moving with different velocity. Okay, so its motion is some of translational and something else. So something else that is called rotational motion. Okay, so most a body rotates in terms as axis of around the axis of rotation. Okay, so motion of wheel, motion of water wheel, giant wheel, so all are rotational motion. Okay, so in case of rotational motion, all the particles rotate about the center. Okay, rotates about the center. So in pure translational motion, okay, velocity of all the particles is same. While in case of rotational motion, velocity of all the particles is not same, but all the particles rotate about the fixed axis. Okay. So if the system undergoes some complicated motion in case of activa, so its motion can be described in simplified way by using the center of mass. So instead of considering all the objects, consider a single point, okay, which is at fixed position, okay, which is at fixed. It means, okay, later on we will discuss. The center of mass of the body is point at which an applied force produces translatory motion and there is no rotation. Okay, it means this point is fixed. Okay, so all other particles rotate about it, but this point is fixed. It means translational motion is possible, but rotational motion is not possible for a particular point. So that point is called, we can say it's a center of mass. Now consider this ruler. Okay, you can balance this ruler. Okay, if you place the finger at a single point. Okay, so here there are two forces which are acting, and these forces are balanced at a particular point. Okay, so the ruler remains horizontal. If we place the finger at any point, then can we balance the ruler? Okay, so could the ruler be in horizontal position irrespective of position of the finger? No, that is not possible. Okay, it means we have to place the finger at a particular point. Okay, that means there is just one unique point at which the entire mass of the body assumed to be concentrated. Because suppose if we consider the mass, then gravitational force, okay, so gravitational force which is acting in downward direction, so this is balanced by upward force at the same point in upward direction. So now this ruler is in balance position. It means whole mass is concentrated at a single point. All mass is concentrated at single point. That point is called center of mass. This point is called center of mass. Okay. So now consider this figure. So now here you can see complicated motion. Okay, so this object revolves about a center, and it also motion is also translational as well as rotational motion. Okay, but you can see at a particular point, at this point, okay, you can see this point. So this point, so at this point, so there is only translational motion. There is no rotational motion. Okay, it means this point, okay, about this object rotate about this point. Okay, so motion, so this point you can consider it as a center of mass. So all the point except one single point do not have fixed path of motion, but this point have fixed path, so we can consider this point as center of mass. So that point which has fixed path of the motion is called center of mass. So instead of studying all the points, we will study only center of mass and consider the body is as a point mass. So if now body is point mass, now you can apply all the Newton's laws of motion. Okay, so center of mass of the body is defined as the point at which the whole mass of the body is supposed to be concentrated in order to study the motion of the body due to an external force in accordance with Newton's laws of motion. It means whole mass is concentrated at single point. So when we apply a force, so that force is applied on center of mass. Okay, and due to that force, the motion will be created. Now motion, so it may be translational motion, it may be rotational motion. But due to concept of center of mass, we are in a position to apply the Newton's laws of motion. Okay, so now consider various examples. Now you can see here this person can ride a bicycle on a rope. Okay, so he has to balance. Okay, so downward force, so that is balanced by upward force. Okay, so you can see the whole mass is concentrated at single point. Whole mass is concentrated at single point. Here also you can see, okay, so here the whole mass is concentrated at our navel. You can see this portion. Okay, so whole mass is concentrated about the navel. So this motion of this is, So this is parabolic path, it may be parabolic path, so rotational as well as translational. So at a single point, okay, at this point the motion is, okay, so you can say, so that is translation. Here also you can see force is acting at this point, okay, and this force or all the forces are balanced by this tick. By using this tick, this person can balance all the forces. Okay, so you can see the importance of center of mass in our day-to-day life. Okay, so because of the concept of center of mass, now we are in a position to apply Newton's laws of motion. So now assume whole mass is concentrated at single point. It means now any object we can consider as a point object, and if object is point object, now we can use the concept of, or we can apply the laws of Newton's. Okay, so now consider this object. Okay, so consider this hammer, and suppose first part and second part. So heavier part and lighter part, wooden and metal iron. Okay, so whole mass is concentrated at single point. Okay, now when we apply a force, okay, so if force or line of action of force is passing through this point, line of action of force is passing through this point, then motion is linear motion, or you can say translational motion. Okay, so now you can see the line of action of force is passing through center of mass, then motion is translational motion. So there is no rotational motion. But if line of action of force, now you can see the center of mass, and line of action of force is not passing through the center of mass. So now in this case, this will create, or this force will create the rotational motion. Okay, so condition for rotational motion, the force must not be passing through the center of mass. Okay, so now your task is find out the center of mass of triangular lamina. Okay, so consider this plate is triangular plate, or suppose for any object you can find out the center of mass. Okay, so there is a specific technique that I will show you in the video at the last. Okay, so what you have to do, so for consider any point. Okay, now suppose hold this object, okay, and plumb with the help of plumber you can find out the center of mass. So for the demonstration I have used the video. Okay, so that you can do it by yourself. Okay, so now consider, so first mass, second mass, and both are attached with the help of this rod. So if we neglect the mass of the rod, okay, then always you will find center of mass of this object which is nearer to heavier mass. So now assume, so this is center of mass, and force which is passing through the center of mass. So naturally the motion should be linear motion. So if force is applied at the center of mass, so system moves in the direction of force without rotating. Okay, but if force is applied below the center of mass, so now object, okay, rotate in anti-clockwise direction. So force applied at a point on the road below the center of mass, system rotates, okay, in counterclockwise direction or anti-clockwise direction. Here force is applied above the center of mass, so now this object will rotate in clockwise direction. So force is applied at a point on road below the center of mass, center rotates counter, sorry, so here there is a mistake. If it is above the, then center rotates in clockwise direction. Okay, so now consider the center of mass of pair of particles. If object is single object, suppose triangular lamina, circular disc, then easily you can find the center of mass. Okay, but suppose there are number of objects, suppose in case of activa, okay, so you can consider body, wheel, handle. So center of mass of independent particle is different, and center of mass of whole activa is different. So how to find the center of mass of whole body? It means it consists of number of body. Okay, so now consider there are two objects. First object with mass m1, second object with mass m2. Okay, and there is a rod. Okay, and assume the mass of this rod, so that is negligible. Okay, so center of the mass m1, so that is you can consider at this point. Okay, center of mass m1 you can consider at this point. Center of mass m2 at the geometrical center. Okay, so now we want to find the position of center of mass of this system. So system includes mass m1 and mass m2. So first identify the coordinate system. So now you can consider coordinate system. So x-axis passing through the center of mass, and you can see y-axis. So you can use y-axis at, you can place y-axis at any point, but if suppose we are assuming here, so at this point, so this is our origin, so you can consider 0, 0. Okay, so with reference to origin, position of mass m1, so that is x1. With reference to origin, position of mass, so that is x2. Okay, and assume the center of mass which is nearer to heavier mass, so you can say position of center of mass, that is xcm. Now we can find the position of xcm. Okay, how? So for that we have to balance the, suppose, forces in case of ruler. Okay, so now consider this is the equilibrium point. So one force is acting in downward, second force is acting in downward direction. So now to balance the ruler, I have to apply the force in upward direction. Okay, so it means I have to balance at equilibrium force. Okay, so similarly, so for force due to mass m1, okay, so I have to consider the moment. Okay, so take moment about the origin. So when we take moment about the origin, okay, then downward force, so I can consider m1 g, then distance is x1. Okay, so motion is anti-clockwise or clockwise, so you can consider this clockwise motion. Similarly, for this object, motion is clockwise motion, so I can consider m2g into x2. Okay, and to balance this, I have to apply the force in upward direction and assume the mass of center of mass. So for that I have to consider whole mass is concentrated at single point. It means total mass I can consider m1 plus m2 into g, so that is upward force, into distance, so that is x cm. So downward force is downward moment is equal to upward moment, or counterclockwise moment is equal to clockwise moment. So now you can see g, g, g cancel. So xcm is equal to m1 x1 plus m2 x2 upon m1 plus m2. So now you can see xcm is equal to m1 x1 plus m2 x2 upon m1 plus m2. Okay, so here this object is placed on x axis. Okay, so we can find the position xcm. Okay, similarly we can find the ycm, we can find zcm. So for xcm we have to consider distance from distance from x axis. It means we have to consider y coordinate. So ycm is equal to m1 y1 plus m2 y2 upon m1 plus m2. Okay, now suppose if I will shift the axis or origin on, suppose, mass m1. So now if I will shift the origin at mass m1, so now I can say x1 is equal to 0 and x2 is equal to, suppose, distance between two objects, you can consider d. So now x2 is equal to d, and assume m2 is equal to 2m1. So m2 is equal to 2m1. So now place here x1 is equal to 0, m2 is equal to 2m1. Okay, so I can say 2m1 x2 is equal to d upon 1 plus 2, so 3m1. Okay, so you can see the position of center of mass xcm is equal to 2d by 3. Xcm is equal to 2d by 3. Okay, it means the xcm which is nearer to heavier mass. Okay, so you can just guess the position. Okay, if your answer is 3 by 2, then from the guess you can say answer is wrong. It should be nearer to heavier mass. Okay, so later on we will shift the position at m1, m2 at another point. Okay, so that we will analyze later on. Similarly, we can find out ycm. Okay, so if system consists of number of particles, so here we have considered only two particles. Instead of two particles, suppose there are four particles, 8 particles. By using the similar principle, we can find out the center of mass. So you can say m1 x1 plus m2 x2 plus m3 x3 upon m1 plus m2. So you can say sigma mi. Here you can consider sigma mi xi. you can replace I is from 1 to n. Okay, but m1 plus m2 plus m3, so that is total mass. So you can say 1 upon m is equal to sigma mi xi. I is from 1 to n. Similarly, you can find for y coordinates. Okay, so you can see for y and z coordinate, you can see ycm 1 upon m mi yi, zcm 1 upon m mi zi. So here we are using rectangular coordinate system. It means we are using x, y and z. Okay, so in form of vector also we can derive the equation. Okay, so later on we will derive equation in form of vectors. Okay, so now suppose consider a special case. Okay, so for here consider mass m1, mass m2. Okay, so x1 you can consider x1 at the origin. Okay, you can consider x1 at the origin, and x2 is equal to d. X2, so here you can consider origin. Okay, and x2, so that is at a distance of d. So now find out the xcm. So already we have considered this case. So origin is shifted to m1, then x1 is equal to 0. So xcm is equal to m2d upon m1 plus m2. Okay, but if I will shift the origin at m2, so now you can consider origin at m2. So now you can consider x1 is equal to 0. No, x2 is equal to 0. So now what is x1? So now you have to consider x1 is equal to minus d. X1 is equal to minus d. And for cm also you have to consider minus xcm. Okay, so now replace x1, so that is minus d. Okay. So if origin is shifted to m2, then xcm, so that is also minus m2, and here you can m1 into consider minus d plus m2 into 0. So xcm is equal to m1d upon m1 plus m2. So you can see the distance. So distance is always positive. So xcm is m1d upon m1 plus. So you can shift the origin at the center of mass also. Okay, so now case 3. Okay, shift the origin at center of mass. So now you can see d1, so that is minus d1. Here you have to consider plus dm. Okay, so now you can consider origin is shifted to xcm. So x1 is equal to minus dm. So minus dm minus 1, sorry, minus m1 dm plus m2 d2 upon m1 plus m2. So this is equal to, okay, m1 d1 is equal to m2 d2. So m1 d1 is equal to m2 d2. So d1 by d2 is equal to m2 by m1. Okay, it means the distance is inversely proportional to mass. Okay, so ratio of distance of cm from the particle is equal to inverse ratio of their masses. It means center of mass, so that is closer to heavier mass. Center of mass is always closer to heavier mass. So now center of mass, so that depends on, so first center of mass depends on masses of the particles, so number of particles. Okay, and second depends on position of particle, on the position of particle. So when we have shifted the position of, the relative position of one another particle. And third, so that is center of mass does not depend on frame of reference used to locate it. So when we shift the origin at m1, m2 or at xcm, okay, but center of position of center of mass remains same. So there is no effect on position of center of mass. Okay. So now you can consider various code. Already we have discussed xcm, ycm. Okay, and if it is located in the space, then you can consider zcm also. So remember this equation. According to figure, you have to use this equation. So from the figure, you have to identify, either you have to find out x, y, z, or another option you can use r. So that is vector quantity. So coordinate of system in vector form. So now consider vector form mass m1. Okay, so from the origin, so its position vector, so that is r1, mass m2, its position vector, so that is r2. Okay, so naturally the position vector rcm should be in between these two. So consider position vector RCM. Okay, so similarly you can find out, so just replace X, Y or Z by R. So here we have to consider in vector form. So RCM is equal to M1R1 plus M2R2 upon M1 plus M2. Okay, so you can see RCM. So here if we are using RCM, then no need to find out separately X, Y and Z. So R1 here we can consider Xi plus Yj, R2 X2 plus Y2j. Okay, so we can get RCM. So RCM is equal to XCMI plus YCMj. So either calculate XCM and YCM separately, then find out RCM, or you can use this equation. Okay, so if it is in space, or if the number of particles are more instead of 2, okay, so now suppose there are n particles, then I can write M1R1 plus M2R2 divided by M1 plus M2 plus M3. Okay, so sigma I is from 1 to n, Mi Ri upon m, upon m. So you can use this equation also. So m is entire mass. Okay, so now you can see RCM. Okay, so sigma Ri. So Ri is equal to Xi plus Yj plus Z. So one video, so that link is missing, I think. Okay, so I will show you the video at the end, or just okay, let us solve first example. Okay, I will show you the video, just hold on please. So now let us see the video.
To find the center of mass of a regularly shaped object, like this block of wood, it's nice and rectangular,
To find out
uniform density, same thickness throughout. The
Okay.
center of mass of an object like this
Object.
is at its geometric center.
Center of
So
mass.
for this,
Inside
I can just take my ruler,
Okay.
I can draw a diagonal from one corner to the other, and draw another diagonal from the other corner. And where the two lines intersect, that's going to be my center of gravity of this object. What I'll do is, I'll just take a nail and I'll insert it into the center of gravity. Now I'm going to take this string that has a weight on it. This is called a plumb bob. Anything I hang it from, this will hang straight down, of course, because of gravity, and that'll show me the direction of down. And now I can see the point about which the center of gravity is directly over, right above that yellow piece of string. If I take the block and tip it, as long as the center of mass stays on this side of the support point, right here is where the block is touching the table, as long as the center of mass is on this side of the support point, the block is going to continue to fall to that side. I'll keep tipping it until you find, and you'll notice that as soon as the string passes onto the other side of the support point, that's when the block will tip over. The next object that we'll find the center of mass of is an irregularly shaped block. You'll see I've cut a corner out of this one, so it's no longer a nicely shaped rectangle.
Now center of mass.
Now what I've done is I've hammered a nail into it so that I can support the block by the nail. I know that the center of mass will always hang below the point of support. If I make it so that the center of mass is not below the point of support, when I release it, it swings back so that the center of mass is always below the point of support. So what I'll do is, I'll take my plumb bob, I'll hang it from the nail,
The center of mass always lie on.
and now I know that my center of mass
Mark this line.
is somewhere along that line. So I'll draw a point where the string is. And then I'll connect that point with my ruler. So now I know the center of mass is somewhere on that line. Now I've moved the nail to another spot on the board. Again, I'll put my plumb bob on the nail. I'll hang the board from the nail, and I know that my center of gravity is somewhere on that vertical line. So I'll draw another dot where the line is. I'll connect the space between the nail and the dot with my ruler. And now I know where the lines intersect. That's going to be my center of gravity. And to check that out, I should be able to balance the object at the center of gravity. And in fact, that is where it is. The object should spin well about the center of gravity. So what I've done is, I've driven a nail right into the center of gravity, and even though this is a very irregularly shaped object, since I know this is the center of gravity, it should spin very nicely about that point. Let's try the toppling experiment with the irregularly shaped block. I'll hang my plumb bob, and I know that the center of gravity now is above a point of support, and the block is stable. If I put it this way, again, the center of gravity is above a point of support, and the block is stable. However, if I put the block this way, you notice that the yellow string is just a tiny bit to the left of the last point of support right here. So that creates a small lever arm distance, which produces a torque, and the block tips over. Here's an interesting object. It's just a piece of wood with a hole in it, and it's beveled to be flat on both ends at an angle. And I can take my bottle, put it through there, and it balances. What does this tell me about the center of mass, or the center of gravity, of this system? Well, I know that the center of mass of the wood and the bottle together must be directly, vertically above this point of support. Otherwise, it would tip over. Here's another one. This little bird, I can balance it right on his beak.
You can see the importance of
So I know the center of gravity of that bird is somewhere on the line, directly, vertically in line with the point of support. In this case, it's most likely below, like the block that I hung from the nail. Here I've got a broom, and I'll put it on my hand, and I can balance the broom. I can feel which way the broom is going to tip, and I can adjust my hand to keep it underneath the center of mass of the broom. And as soon as I stop doing that, the broom tips over. This is similar to the way a rocket fires. As the rocket launches, sensors in the rocket detect if it's tipping side to side, and small rockets fire on the side to keep the center of gravity of the rocket over the thrusting force and keeps the rocket straight as it rises through the air. Another vocabulary word that we'll look at is the word stability. For something to balance, of course, like we mentioned, the center of gravity of the object has to be above the base. Not only this way,
center of mass is
but also this way. And the higher up the center of gravity is, the less stable the object is. Okay? I'll still balance it on a thin edge, but I won't make it so high. Now I can tap it. You'll see it wobbles a little bit, but it doesn't tip over compared to this. Just the slightest touch, and it tips over. Of course, if I put it this way, that's going to be the most stable of all. The center of gravity is very low, and the base is very large, and I can't tip that over. Here I've got two plastic cups. The first cup is just a cup by itself. The second cup has a ping pong ball glued into the bottom of the cup. What I'll do is I've marked a black line on each cup, and I'm going to take some water and I'm going to fill each cup up to the same level. So each cup will have the same level of water in it. Then I'll tip the platform and we'll see which cup tips over first. Which cup do you think will tip over first? Okay, so let's fill the cups with water up to the black line so that both cups have the same level of water.
Think about
Now ask yourself, which cup has the higher center of gravity?
The center of mass is at higher level.
And remember, the higher center of gravity means less stability. So as I tip the board, and we see that the cup with the ping pong ball in the bottom had the higher center of gravity. Because down here where the ping pong ball is, that space is filled with air. So more of the mass is higher up than in this cup.
Mass that is at higher level. Okay, so now I am sure. Okay, concept of center of mass is clear. Okay, so in the next lecture, now we will solve example, okay, based on center of mass. So thank you very much.